Greetings, everyone. My name is Dachuan Shi. I'm a research scientist at Fraunhofer Institute for Production Automation. Today, I'm very happy to present you our recent work, a set administration share-based flexible manufacturing system. First, as a background information, the concept and the requirements of flexible manufacturing will be introduced. Next, we will explain the fundamentals about a set administration share as a standardized solution for digital twin. Our approach is to use AES language for information modeling to achieve flexible manufacturing. Finally, we will give some details of implementation and demonstration. The paradigm shift from mass production to mass customization requires faster market readiness for products, short product life cycles, and more product variations. As a result, the manufacturers face the challenge of economically producing individualized products. Existing automation technology, however, has very limited support for flexible production. Manufacturing processes are very complex and consist of a large number of dependent production steps. The change in one step may result in unwanted effects in other steps that cause error. Therefore, the process of setting up automated production or changing it is labor-intensive, time-consuming, and very expensive. More precisely, flexible production means manufacturing of different products or recipes on the same production line, or dynamically adding, removing, substituting production devices or their tools, redeployment of the software or firmware. A production system that can meet these requirements is called flexible manufacturing system. But how to achieve flexible manufacturing has been rarely explained. For this purpose, we propose a set administration share-based flexible manufacturing system. Among others, we mainly focus on decoupling production process from production resources and decoupling the functional rules of production resources from the physical set. What does it mean? Typically, the manufacturer usually furnish a product order configuration tool that allows the customer to specify individualized product orders and make product requests. Once receiving the product request, a production order is generated in the ERP system. In the phase of the production planning, the product order is transferred into a production order, where the production processes are divided into a sequence of process steps. We call it bill of process. One process step is defined as the process segment in the IEEE standard. It should contain the information of the required production resources, namely production equipment, materials, and the qualified persons. Conversely, each process step or segment is directly associated with the corresponding production machines. If this machine is not available, then this production step has to be pending, or the reassignment of this production step to another machine has to be manually done by the production manager, who must be very familiar with the actual status and capability of the production machines and persons. What we intend to do is to decouple this process segment from the physical production resources. So we introduced a virtual entity called functional rule or rule-based equipment. That means we introduce two kinds of abstraction. A physical production machine can be abstractly represented by its functional rule within the production line, based on its production capability. On the other hand, the requirements can be derived from each process segment. Now, the assignment of a process segment to the production machine becomes a matching task, matching between the requirements and the provided capability. In this way, the flexibility is increased due to this abstraction, because the matching can be automated by the algorithm. And furthermore, a physical machine can be replaced by another machine, which provides comparable capability. So this is our concept to increase the flexibility. The next question is how to realize this abstraction. As mentioned, we use the so-called asset administration shell. So AES is a standardized solution for digital twin proposed by Germany. Now, the government and the industrial associations are promoting this concept AES to the international standardization organizations such as IEEE. Someone may hear about a reference architectural model for Industry 4.0, or in short, the HARMI 4.0. AES is the implementation of the HARMI regarding information modeling. Today, when we talk about the digital twin, I suppose to most people, it often refers to a kind of a 3D animation model for simulation or visualization. But the digital twin, as it is defined, is far more than a 3D model. In HARMI, physical set is accompanied by its AES that contains an interoperable information model to represent these physical sets in various aspects, covering the entire life cycle of assets from conception to recycling. Assets can be physical machines, products, process, or IT service, etc. So it does not have to be a machine. The key word here is interoperable and the various aspects. Various aspects means for different purposes, in different user cases, we usually need different information about the assets. In AES, the information in different aspects can be carried by so-called submodels. For instance, the submodel digital nameplate carries the information for identification. The submodel technical data is for the technical specifications of the assets. In this way, the AES-based digital twin can represent any required information of assets, rather than only a simulation model. In contrast, a simulation model itself can be a submodel of AES. The major advantage of AES is that it ensures interoperability and unifies the namespace regardless of software applications, enabling both vertical integration within enterprise and horizontal integration across the value chain. So this interoperability is mainly achieved by using standardized submodel templates and semantic identification. So the meta model and the specification of RIS has already been standardized as the IEC standard in the last year. And the submodel templates are now developed and standardized by the so-called Industry Digital Twin Association, IDTA. The company like Siemens, Bosch, Microsoft, Festo, etc. Are all the members of this organization. The industry people and the university and the research institute sit together to develop the submodel templates. As a result, as a summary, the AES looks like this diagram. It has a Unicode identifier and also contains the identifier of the represented assets. The information is carried by various submodels, depending on user cases. It provides APIs such as MQTT and REST API that can be invoked by other software applications to fetch or fill in the information and data in the AES and submodels. Now we have an overview of AES and the submodels. How we can use AES for information modeling to realize our goal for flexible manufacturing. Below is the information flow of the proposed AES-based FMS for production planning and control. For production ordering, the product-related information can be provided by a predefined AES of the product type to the customers. The AES distinguishes between instance and type. As mentioned, once a product has been ordered, the AES of the product instance is initialized. The product order, the production order, etc. can be modeled as submodels of product instance AES. Taking production order as an example, in the AES meta model specification, Several classes are predefined as the so-called submodel elements, such as a property, a reference element, a file, blob, operation, etc. Each type of this submodel element has its own functionality. They are the basic building blocks for information modeling with AES. The most common one is the property. For instance, the production order, production type, etc. are defined as the properties. They can have different value types. Um, the the real measurement or int or a string, whatever. The reference element can be used to refer to other submodels. For instance, in this submodel, product order and the bill process are referenced, but the content of them is defined in another submodel. Similarly, a bill process is composed of multiple production steps, each of which can be predefined as a process segment. In a process segment, the requirements for the needed production resources must be included in this submodel element collection. 3 holes on a shaft is a general process step and can be defined as a process segment, for instance, which requires a drilling machine with certain specifications and tools, a qualified worker for operating it, as well as a chef as the material. To produce a particular product, this process segment will be installized, such as drilling 3 holes with diameters of 20 mm on the left side of an aluminum motor shaft. The information on the workpiece, such as material, dimension, and the required tolerances, can be regarded as the requirements of the role-based equipment for the subsequent matching. The functional rules of machines or the role-based equipment is abstraction of physical machines. Its AES mainly contains a submodel role capability to describe its production capability. The capability is described in different aspects, such as semantic ontologies, natural language description, technical specification, reference workspaces, and the capacity. The capacity is described in another submodel, so-called equipment capacity, to indicate the actual working capability and availability of the equipment. Now we have every piece of information for production planning. Matching the requirements with the equipment capability can be done by algorithm. In this way, the planning process can be automated. Moreover, if physical machines are not available, this functional rule can be assigned to another machine with equivalent capability. We implement this approach using different tools. The AES modeling is done by using AES Package Explorer, which is an open source tool developed by the organization IDTA that I mentioned before. As can be seen, the physical assets has two AES. One represents its physical characteristics, which is typically given by a machine supplier. The other one is its functional rule in a production line, containing the information such as the location, capability, and the OPCUA server information for monitoring. The data integration is done by a self-developed middleware called Manufacturing Service Bus. It hosts the AES server and the register, containing the static AES and submodels. The dynamic ones can be hosted at the edge side and made accessible via the AES register to provide access to other software services. MSB connects the machines at the automation and field level via various standard protocols such as OPCUA. Explanatory software services such as MES and ERP can be integrated within MSB through appropriate adapters. In this implementation, InfluxDB is employed as a database and connected to the MSB, so that the field data collected by OPCUA server can be directly stored in the database. Also, the AES themselves can be stored in the database. So this implementation also involves basis Java SDK for AES. We demonstrate this approach on a Festo demonstration called CPLab. It represents a sheet metal stamping machine that can punch the workpiece surface into a specific shape based on the stamping die. The demonstration mainly consists of a conveyor system, the workcell for press tending, and the workcell for turning over. Each workcell, along with the associated conveyor, is driven by an electro-pneumatic system controlled by Siemens PLC and can be operated by a HMI panel. OPCUA server is established on the PLC for data communication with MSP. The OPCUA node space is visualized from the OPCUA client perspective, as shown in the middle screenshot, and the right figure shows integration results in the user interface of the MSP. So the following screenshots shows the MSP dashboard to monitor real-time data flow and the logs, and the InfoGB dashboard to monitor the actual status data of a compressed airflow within the pneumatic-driven drive system. Basically, this demo shows the production control and how the AES works together with the OPCUA for condition monitoring for this purpose. We did not find a way to simulate ERP and math system, so we did not demonstrate the process of production planning. So this will be our future work. Finally, conclusions. The AES-based flexible manufacturing system was proposed to improve the fundamental flexibility of a production system by decoupling the physical sets from their functional rules and decoupling the rule-based equipment from the production processes. So this can be achieved by AES-based information modeling and results in flexibility in production planning. For production control, the AES can work together with the standard protocols such as OPCUA and bridges the data from the field to the MES and further to the ERP system. Notably, the current work lacks the implementation of algorithm for capability matching, and the demo for production planning is also missing, which will be addressed in our future work. Thank you very much for your attention. So unfortunately, I cannot travel to Wuhan. So if anyone has any questions, you can reach me per email. Thank you. Bye-bye.